Hi, my name is Joe Chacon. I'm an electrical engineer with Padge LLC. This is the ninth of several videos about harmonics. Today, I want to talk about software devices to evaluate harmonics. There are a few software packages out there. Our company uses one called Easy Power. I'm not endorsing Easy Power nor discriminating against others. It is the one our company uses mostly because we're very familiar with it. Let's dive into it. Okay, so we're into Easy Power. I've made this model. This model is a good representation of a system where you have a bunch of motors and a bunch of drives, but there was never any current limiting line reactors ever put in place or any type of filters whatsoever. So you can see they're all here. And here's how I modeled the harmonic content of each one of these variable frequency drives. So there's different libraries within Easy Power. You can just pick your manufacturer, pick your type, click import, it just carries it over there. So it tells you the percentage of current based off the fundamental. In this case, it was 14 amps. And it tells you the angle that that current began with respect to. I have a transformer, 250 kVA, a little bit of impedance on that. Have a utility, not very strong, about an average size utility. I did not model any harmonics in there. You can, I'll show you where you can do that. You can just populate it from the table or just use it from here. Usually you could get this by measuring it, and that'll be on another video. But it's kind of confusing in some ways. I'm just going to do short circuit values here. And I have a point of common coupling. That's very important. The point of common coupling is what's used for the IEEE 519 analysis. So if I go to harmonics on my point of common coupling, which I'm defining to be this breaker here, I want to monitor this as the IEEE 519 point of common coupling. My kVA that goes through this device is 164.8 kVA. I was able to calculate that and actually did that with a power flow from there. And then I calculated my short circuit. I did that through this short circuit focus. And I knew my load, so I divide that and that gives me the ratio of short circuit to load current. All right, so that builds my model. Ignore this right here. This is for the second part of what I'm going to do with the active filter, and I'll talk about that in a minute. So you go into different focus modes. So you have power flow focus, coordination focus, things like that. With Easy Power, that's what they call them as focus. So I go into harmonics focus, and I want to look at my harmonics. So I go through here. These are some tabs here that I'll get through in a little bit here. But the one I really wanted to show you was the harmonic report. So you can select what type of report you have. The one I really care about the most is the IEEE 519, but I can look at all kinds of other stuff going on in there. I'm going to uncheck these, and the ones I'm just going to show here are going to be K duty or K factor and conductor derating, because those are two things we talked about in previous videos. I'm going to click apply, and it says report option changes will take effect on the next solution. So what does that mean? That means you have to click this button right here, summation. And you got to do that every time you make a change because it recalculates it. So I click summation. I want to see my report. I go under window, harmonic summation report. And here we go. 27.29% of total harmonic distortion on my current, 7.318% for voltage. Transformer was a K factor of 3.478. It's only good for 76.4% of its nameplate. And all these conductors have a capability derating as well. Okay. So we know we have harmonics in our system. We know we want to mitigate it. We know it's going to probably be cost prohibitive to come in here and each and every one of these drives and put in a reactor. So we put in a active filter. And I want to talk about how to size that in Easy Power right here. The way we size that is by we put in a shunt. And that shunt is basically almost a short circuit with just reactants. So I've defined that here. And I want to close this in. And now I want to look at my harmonic content and which direction is it flowing for each and every one of my harmonics on the 5th, 7th, 11th, 13th, 17th, etc. So I go back to my harmonic focus. I want to go to all source. And what I want to do now is I want to open up that harmonic options tab, click control, and let's start by looking at each current flow for each harmonic. So I'm going to put it on the 5th here, click apply, and you can see 40.03 amps of harmonic current on the 5th harmonic. Notice the direction of arrow here. 7th, apply, 27.52. The 9th is a triplet, it'll be 0. The 11th. And I'm going to just keep doing this all the way through the 49th harmonic. Write down these values. And then those are going to be the compensation currents for each harmonic that our active harmonic filter is going to inject onto the bus, canceling out the harmonics that are there. So let's go look at that right now. Open that guy back up, close this guy, and I want to look at my active filter. So the way I do that is I just make a load in Easy Power, and I open it up, and I go to Harmonics, and this right here will be the size of the filter. In this particular case, I started with 100 amps just to see if this is big enough. The ones I work with sometimes come in increments of 50 amps, 100 amps, 150, 200. Then if you need more compensation current, you can put them in parallel, because notice they did go in as shunt devices. All right. So all those numbers that I got from this shunt analysis, I put those in right here. And notice they're in percentages. So when I was looking at them before, they were in currents. Now I have to put them to percentage of my fundamental, which is 100 amps. And then I have to put in the phase angle to completely cancel out the harmonic. So in this particular case, it was 180 degrees. So to cancel it out, you have to subtract 180 to 0. For the 7th, it's coming in at negative 180 degrees. So I subtract 180 and I get negative 360. I hope that makes sense. Okay. So now let's go to harmonic focus and do a summation. And I want to look at ITHD. You can see that for this system, the most amount of compensation current I will need is 54 amps. So as electrical engineer, you may decide, I don't want 100 amp active filter. 50 amp would be fine. And you'd probably be okay in this situation for that, because are your motors going to be running all the time? Are they going to be mechanically loaded at all times and things like that? So, that's the case there. But let's look at our harmonic focus and let's look at the report. So I click summation. I'll do it again just to make sure I did. And I open up my report and look at that. These harmonics have essentially gone away. Our active filter is working. And we know that if we were to put one in, we would cancel out those harmonics, as you can see in this report right here. Look at our K duty of our utility transformer. Goes back to 1. It's good for 100%. That's what we want to see. I hope this knowledge can help you become the harmonics guru in your company. Please look us up at padge.org. That's padge.org if you need anything else on this topic.